Okay, so today we're going to do stochastic gradient descent on linear regression, just to show you the logic behind it. And before we do that, who's done with the SVM part of homework 4? I mean, who's struggling with it, or rather, like, who's stuck? Okay. Homework 5 is out. I just have to add it to the assignments. It has ridge, lasso, logistic regression, and Q-learning. So Q-learning, you have the tabular case, but I added around 18 bonus points on logistic regression and Q-learning, so you have a chance to catch up if you missed something in the last homeworks. And logistic regression is just an analogy to what we're doing today with lab 4, with lab 5, with just the gradient changes, but the other things are pretty much the same. Okay. So I'll just go briefly through lab 4, some components that I think most people are struggling with in homework 4 currently. And yeah, so lab 5, it will be the same thing as the last lab. We try to cover as many questions as we can, and the rest you have to continue or finish by yourself. Okay, let me just... Okay. So last time we had all of these, but I think the tricky part for most people was how to compute the predictions and how to compute the intercept. I've already provided how to compute the intercept, so you can just check that formula. I can go through it again briefly. Okay. So last time we said support index, it just says SVM support. Those are the indices of positions where alpha is strictly greater than 0. And alpha in SVM, in scikit-learn SVM, is different from our alpha from the homework. So basically here, so I'm going to call it alpha SVM. Alpha SVM, which is the scikit, is our alpha multiplied by y, okay? And then we just take in the support index, okay? So to imitate the same alpha we have in the homework, we can do MP absolute, okay? I just want to print these. Okay. So just to make sure everything is good, because I've seen some people who just copy-pasted the formula of intercept from last lab. So the shape of alpha here is one column, okay? So to make sure we have the same shape, which is just 1D array, just take index 0, okay? So in this case, alpha is going to have 8 elements, and support index is basically 8 elements. All right. So this is the formula of the intercept. So I assume I have k. So make sure things make sense for you. We can just do k. This is returned by the kernel, right? And I'm only interested, when I compute the intercept, I'm only interested in the rows or in the columns where that have the same indices as the support indices. So I'm just going to do k equal k support index. So this is how you do it in NumPy if you want to take, okay? And the rest is the same. I'm going to do y support index minus, so let's create the second sum, or the internal sum, before we move to the outside one. So in the inside one, we have alpha. We're going to multiply it by y of support index. And we're going to multiply it by k. Okay? Let me just show what intercept is to make sure things make sense. Okay, so it's an 8 by 8 matrix, right? So now I have alpha multiplied by y multiplied by k. I want to sum the rows, okay? So I'm going to just do sum. I'm going to sum this quantity over the rows. Sorry, NP sum. And here I'm going to do axes equal 0. Okay. So now I have to have, if I do this sum, I'm ending up with 8 entries. And I'm just going to do the same thing, y over the support index. I'm going to have 8 entries. I can check the values. It should be close to 0. No, it should be, I mean, the values should be pretty much similar. So here, this is the mistake I made before. And why these values are not close, because the axis here I've chosen was wrong. I have to do 1. Because when I multiply 1D array by a matrix, okay, I'm basically multiplying the column-wise and not the row-wise. Yeah, so when I do this, the values are much closer, okay? But it doesn't matter. Why? Because at the end, I'm just going to take the np.mean, right? So I'm just summing everything. I don't care whether I'm summing the rows first or the columns first. This is slightly closer to the intercept or the B that we got before. Yeah. So the last time I told you they take the minimum, that's not true. They take another formula that has to do with the minimum and the maximum. If you want, I can show you the snippet of the code, but it's much more complicated than min and max. Sometimes it's min, sometimes it's max, depending on the values that we get. Okay. So basically, they will just take the values that we had before we applied the min, and then there's a bound on that, depending on the sign and everything. But for this homework, just keep it simple. Just taking the average is very close to what SVM is going to have. Okay. So now we have the intercept. The question here is, I want to compute the predictions, right? So let's do that. To cell. So in the prediction, I should compute, let's say I want to compute the prediction for all elements in X, okay? So in this case, I have to compute the kernel between the support indices and my X from the training, okay? So in that case, in the homework, it's going to be self.x. Sorry. Right? For me, just X. I'm going to call X test. Let me generate some new points. Yeah, let me call it, yeah, I'll just call it X2. I don't want to mean. X2 equal the first 4 rows of X. So here I have to compute the kernel between the support indices. So I just copy paste this one. I don't care about the, here's going to be 2. And I'm just going to take the rows of support indices. And, or to make it simple, I can just call it XS equal support index, okay? So here's going to be the kernel between my support vectors and the ones I want to predict for, Perfect. Okay. So the formula then is pretty much the same. I just have to move the sum that I have here to the other side. So there's going to be b, and I'm just going to remove the sum. So if I write it, okay. So here I'm summing over the support vectors. So I'm going to call it y hat, usually. So let's compute this sum. I'm going to do alpha, y, and then multiply k that I just got. Okay, so it's going to be y of support index, because those are only labels I have. Let's multiply by alpha, and then let's multiply by k. Just here, I expect I get an error. Yep, because as I said, it's column-wise, so I can just do transpose here. Okay. So if you want to see the shape, it should be 4 by 8, if I'm not mistaken. Yep. So it's 4 by 8. I'm summing over the support, so I'm just going to sum over the second axis. It's going to be 1. And then I'm going to add the intercept that I just got. And this should be my y hat. Okay. So this formula, it applies for all types of kernels. Okay. Last time we said that for linear kernel, you can show that this is basically equal to wx plus b. Okay. Because this thing here, just the xi scalar x, and w will be the sum over alpha I, yi, xi. Okay, so I'm just going to check the prediction I got with the prediction that we get from the solutions from scikit. Okay, so I call it like it's going to be it's going to be xs dot w plus b. Something is off here. So what am I doing? I need to have, x2, sorry. Yep. Okay. So these are the values I get using my intercept. If I use SVM intercept, yeah, we get the same thing. Okay. Make sense? All right. So now you got the SVM problem in Omok 4 for free. Assuming I guess not everyone is here, so some people miss it. Okay. All right, so we're going to move to the stochastic gradient descent. Yeah, you can ignore this intro because it says that the helper functions are the end. I just moved them to the beginning here. Okay. I'll try to go slow on this. So if you have the notebook on your laptops, you can try to work on it. Otherwise, we'll be finishing the lab before time is up. And I want to give you some chance to have some participation points. So this is very similar to what we have done before. If you remember the sigma following some Gaussian, yeah. I remember we did some cosine something or sine multiplied by cosine of something. So, yeah. So basically here, x is x trained and x valid, and we want to compute y. Note here, we are providing sigma squared, okay? So we are providing this parameter here. The rule is if epsilon follows a normal 0, 1, then alpha epsilon follows normal 0 alpha squared. Okay. So in Gaussian mixture models, the formulas that we had were for sigma squared. But to get sigma, we had to apply the square root. Okay. Is this clear? Okay, if it's clear, I'm going to just do it myself. It's going to be x train plus MP, sorry, yeah, just do MP random, I'm not sure if this is going to work, but let's see, n multiplied by 6 squared, 0.5. Okay. Here's going to be the same thing. I'm just going to change x train with x valid, and I have to change how many entries I get. So here's going to be n by 4. MP is not defined. Okay, I have to run this. Yeah, I have a typo here. Come on. All right, so this is our data. I think so far, yeah, we have worked on regression. Yeah, we had the classification data and we have regression data. Okay. Yeah, I think this is just redundant. I can remove it. So this is one-dimensional data. We have one feature, okay? And the true values are the y-axis. We're going to use the same trick we used before, which is we're not going to learn the weights. So here we're going to do linear regression. We're going to try to fit one single line for the regression. We're not going to try to learn the weights and the intercept separately. We're going to learn them at the same time. And the trick was we're just going to add one, a constant 1 to the features. So we're going to just add the column in this case. So we're going to do the same thing here. We're going to do MP column stack. So I can do MP once like x train. Here I can do x train because I only have one column in x train. Usually you don't want to do this because if you do this, if you have 10 features, you add in 10 constant columns. So in this case, we have one feature, we can do this, but usually you want to do MP1's shape 0. Okay, and then let's do x train. X train is not defined. Was it? Yeah, it was lowercase. I'm going to do the same thing with x valid. So it's going to be valid. And valid. We can investigate like the first columns of the first rows. And x valid should be around the same thing. Okay. All right. So now we're going to fit the linear regression. So you are going to implement linear regression with ridge regularization in homework 5. For lasso, we're just going to use scikit-learn lasso. Okay, solving the problem with lasso regularization is a bit tricky. Okay, so we're just going to use it. It's outside the scope of this class. So for lasso, you're not going to do any from scratch coding. So in this case, we just tell the scikit-learn model, don't fit the intercept, okay? Because we're saying that we add in the constant column. So in this case, the intercept will be just the coefficient, the zero element of the coefficients, okay? There you go. So in this case, the intercept is 0.90, blah, 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 and the weight is 2.2. Okay, makes sense? If we don't want to do that, we can just do, we're going to check. Let's check if this makes sense. I'm not going to use all the columns, so I'm just going to do everything, but from 1 onwards. And I'm going to print and intercept. And here, fit intercept is going to be true, okay? There you go. Okay, so if we just use one feature, it's the same problem. I mean, it's the same formulation, just implemented differently, okay? So we're going to stick with the first one. Any questions so far? Okay. All right, so what we're going to do in this function called plot surface is we're going to vary the values of the intercept and then the values of the coefficient, okay? And we're going to plot z, and z in this case is the squared error, the mean squared error, okay? Let's code it differently, okay? So what's happening here is that we are taking values of x, which we're going to play the intercept between -3 and 3, and the values of y, which are going to be the coefficient, is going to be varying between -1 and 5, okay? We have used this mesh grid trick before, I think homework 1 or lab 1 or 2. So to make this formula much simpler, I can just do x. Let's do this. I'm going to do weights. I'm going to call it weights. MP column stack. And I'm going to use x, going to be my intercept, and then y is going to be my coefficient, okay? Then the prediction will simply be x dot weights. This is transpose, why? Because x is going to have two features, and weights is going to be something by 2. So I just do transpose to make sure that everything that I do there makes sense, okay? Okay, so now I'm going to do x, this is y, minus, and then squared. Okay, so my z will simply be the sum over all these values. Okay, so we're just going to sum it. This is more like squared error, so I'm going to call it SE. Perfect. Okay, so this is basically what this formula is doing. All right, so this is the shape we get. So on this eclipse, we get in MSE around 200. So the optimal value is basically the center here. So the more we move to the center, the more we get closer to the optimal parameters. Okay. This is more like a level map, if you're familiar with topography maps. Okay. So lines here means that we are at the same altitude. In this case, we dig in deeper, so we want to minimize. It's more like a hole. And I think these are called surface or level curves or curvatures. I'm not sure. Okay. So for B0, which is the intercept, we remember it was like 0.9. So it's going to be around here. And the optimal one was 2.2. So it's going to be, yeah, the center is exactly what you expect it to be. So what we're going to do is, instead of learning the exact solution, we're going to use stochastic gradient. The advantage of stochastic gradients is that you don't need to have the exact formula of the solution. All we need is the gradient of the objective with respect to the parameters we are optimizing. Okay? So remember, here we're trying to minimize the true labels minus the prediction. So it's going to call it, let's call it AX. So it's basically WX squared. If I compute the derivative with respect to W, I'm going to get 2 of Y minus W X, okay? So it's going to be some transpose somewhere. I think transpose should be here, but we'll see how it works, okay? So the gradient gives us at which direction should we move to minimize the loss. Sorry, this is to maximize the loss. So if we want to minimize, we have to do the minus. So we have to take minus that gradient. And this is exactly what's happening here. In the formulas, we're updating one at once. So what happens there is that we're saying that x is equal to 1 small x, since we're adding the constant, okay? So the formula here becomes 2y minus 1x is going to be x multiplied by 1, so it's going to just be this. And the second one is going to be 2 of y minus, it's going to be small x, so w, sorry, this is w1, this is w2x, and this is x. Okay. So we're just expanding that one to the element-wise updates. All right. So eta here is a parameter that we call the learning rate or the step size. And that's basically reflects how large the jump that we want to take. We're going to see how it affects the learning problem that we have. So now, one common thing to do is to shuffle the data before we apply stochastic gradient descent, because we are taking the updates with regard to each sample. And the problem here is that if you keep the same order, you basically give in you might give more importance to the first samples in the data set, which might have a large gradient. So when you're shuffling, you're basically taking some sort of averaging over the gradients from different samples. So I'll give you 7 minutes to work on this or think about it, and we're going to move forward from there. So we're going to shuffle the data, and we're going to update the parameters. Okay, we can do it element-wise. I'm going to show you how to do it just directly without doing the indexing here. Any questions? All clear? So the poll about homework 6, I saw most people chose forecasting, either stock prices or climate. Almost no one specified which one, so I assume it's climate. We're gonna do a competition using some wildfire data. We're gonna see if we get some satellite data, then we can do some deep learning. Otherwise, we're gonna try to use other models. But you're gonna see that in homework 5, and the bonus question of Q-learning, there's deep Q-learning where you're gonna use Keras, so to train a neural network for the Q network. I don't expect you to know how to use it, but the next lab, we're going to start deep learning, so I'm going to introduce you to TensorFlow and Keras, so you get basically 1 week to work on it if you start from there. Yes? In the competition, you're free to use anything you want. Yeah. Just in the class, we're going to just keep it Keras. PyTorch is good, but if you're just starting, there's so many things confusing, like the shapes, the types, so just keep it simple. We're just going to explain what's happening behind all those calls, and yeah. But if you want to use PyTorch, it's up to you. In the competition, we're just going to be evaluating based on the predictions. That's it. You can use anything. Yeah. So if you have seen the rules, I can go over you're going to read them, but you get plenty of chance to catch up on previous homeworks. So the top 25% gets 10 plus 10 bonus points, and then we're going to give you another bonus based on how good you do, okay? So you're going to set a threshold for each score, but once you go beyond 100 out of 100, you're going to get some bonus points for that. But we estimate that it's going to be up to 30 points, bonus points. So if you work hard on that, you can catch up basically on participation points if you missed one. Okay, let's do this. So what's happening here is that we're computing the difference, and this is basically this element here. This is what we call difference. This is fine, but usually I just like to multiply by beta. Okay. and then this is going to be sum. Sometimes, yeah, it depends on the how recent NumPy version you have, but it should work. Okay. So once we have the difference, we're just going to multiply by x for beta 1, by the value, which is the second column of beta 1 and beta 0. So let me just explain what's happening here. This basically diff 0 multiplied by beta 0. But we know diff 0 is 1. Okay? Sorry. Diff 0 multiplied by x 0. But we know that x index 0 is 1 because we added the constant column. So we don't need that one. All right? So this is the difference. We're going to multiply by x. We're going to multiply by 2 coming from the power there. And we are trying to minimize, so we have to subtract the gradient. Okay? But we're not subtracting everything. We are taking a smaller step. And that smaller step is eta. Okay? That's the learning rate. So it's going to be minus, it's going to be beta 0 minus 2 multiplied by eta multiplied by the difference. Okay. The same logic here. We just have to make sure we multiply by the feature. So for consistency, I'm just going to write it so if you look at it later, you understand what's happening. Okay, so this is 0. And here's the same thing. The only difference is we're moving to index 1. Okay, we're working on the second column. So here's going to be 1, 1, and then 1. This is fine. It's not wrong. If you want to be NumPy-ish, you can just do beta equal beta minus. And you can remove this. Okay. It's the same. Either use the first two or the last one. Should be the same. Yeah, let's shuffle data first. So I can call it permutation equal np random. Here is going to be permutation. And how many elements we have? We have x dot shape dot 0. Okay? So now we're just going to apply this. I'm going to do x equal x permute. And I'm going to do the same thing for y. Okay? I see a lot of people, they just shuffle x, but they don't shuffle y. Well, in that case, you're just scrambling the features, but you're not matching them to their correspondent labels. So that's why when you do permutation, you have to keep track of this. I'm sure there are some functions you can use that do those for you, but I'm just saying if you want to do it yourself, you can do it this way. So if you're going to shuffle, you have to make sure that the shuffle is the same for the features and the labels. I have a problem here. Okay. Okay, so I don't have to do this here. I can just do permute and use it directly. You're going to see this in homework 4 in logistic regression. We're going to use the same trick. There you go. Okay, so here we're starting from initial value minus 2 minus 1 for beta, minus 2 minus 1. And we're using a learning step of 0.0, yeah, so it's like 2.5 to 10 minus 3. Okay, so you can see here the closer we get to the optimal, the smaller the gradient gets, okay? And you can also see that if we use a very large learning rate, if we follow this gradient, we might end up here. So this is the advantage, or basically this is the thing that we have to tweak when doing stochastic gradient descent, is you want to make sure that the learning rate works, basically. Because if it is too small, after 100 iteration, if I just take some baby steps here, I might end up just here. If I take 100 steps, if the learning rate is too small, I would never reach the optimal. If it is too large, I might be just jumping around, okay? And so there are ways to tweak that. We're not covering it in the homeworks. I'm not sure if you cover it in class, Adam regularization or Adam optimizer. If you're interested, I can put a problem on that, how you can implement your own, we call it like a stochastic gradient schedule. And the idea here is that you also, when you do the training, you monitor the size of the gradient, and you want to make sure that it moves smoothly and doesn't go around, okay? Because the problem here is that if I follow this with a large step, I'm going to end up here. Then if I compute the gradients, it's going to be this side. So you can see that the gradient position changes drastically. So one way to counter that is to take an average of the gradients, not just take each step, but keep track of the last jumps and take an average of those. Okay, that's what we call moving average. So you want to smooth. You want to take a smooth smooth step at each time, and that's basically what Adam is. It's called adaptive moment. I think adaptive moment gradient, something like that. Yeah. So the rest of the problem, we just be playing with the learning rate and see how it affects all of these things. Okay. All right. So I'll let you do SGD, which is exactly the same thing we've done before, except last time we used indices for beta 0 and beta 1. So here we're just going to say we're going to do it for any number of features. We don't care what the number of features is, okay? And I already done it, actually, okay? It's just this one. So this problem is just going to use this and this. I mean, the beta 0 and 1. And here, we're just going to use the other one that does not use the dimensions. Something is off. What is it? Yeah, maybe the indent, okay. So yeah, the different, oops, I have a bracket missing here. Yeah, this should be the same thing, nothing different. Just using different logic. Any questions? All right. So I'm not going to spoil part 3 for you. I'm going to let you play with it, but let me just give you an intuition of what's happening. So let's just see, I'm going to do the same thing, but let's just vary eta and see what happens. There you go. So last time we used 2 to minus 2.5 to 10 minus 3. Here it's just 0.1. You can check that the step we are using here, or basically the direction we have here, is the same one we have here. Okay? Or is it? It should be. All right. But once we move beyond that, we basically get in some unstable path towards the optimal. It's very difficult to see, but maybe we will reach in the optimal. So let's see here. Let's go to just look at the values of B hist, the histogram. And let me take the last 10 values. Yeah, I mean, we're getting close, but yeah. So the last values are much closer to the optimal. Okay. So let's do this. Let me just take the last 20. Yeah. Better than all that mess we had with all samples. All right. So in 3, we're going to tweak 2 things, which is how the optimal value or the optimal parameters that we reach, what's the function based on the learning rate. And then we're going to also discuss, or basically you have to analyze what's the link between the loss on the validation data and the training data. Okay? Because the problem in stochastic gradient descent is, what is the stopping criteria? When do I stop? Usually you stop, you say, okay, I'm going to stop if the MSC does not improve for a certain number of instances on the training data. But then the question there is, does that translate to the validation data? So here it's fine, because the 2 data sets are pretty similar, not too noisy. Well, actually it is noisy, but yeah, it's pretty similar. So the training and the validation should translate. I mean, the optimal on train should be very close to the optimal on validation. But that's basically what you're going to be required to do on the remaining part. Okay? Any questions? Does it have to be related to the hands-on? Okay. Okay, so we have like 70% people responded, and 63% on forecasting. Okay. So the data set we're going to have for the homework 6 is not going to be public, so just don't worry about finding some open source models. But just in case it happens, you're not allowed to copy some people's solutions. Okay? It's a challenge. We want you to explore all the things that we have covered in the class. And yeah, you also get some bonus points based on the approach. So if you use like Notebook or Python, make sure the code is clean. I suggest Notebook because you can present your thinking process and all the things that you have explored. So the quality of the notebooks that will generate the solution will also be evaluated, and you can get bonus points on that. Okay? But that's for the next homework. So now you just have to worry about homework 5. We're going to launch homework 6 a little bit early, so you get time to play with it. And yeah, that's pretty much it. So the last weeks of the semester is going to be less stressful. You can concentrate on the exams. That's pretty much it for today. So remember, I'm going to create an assignment for this one, so you have to submit it as well by Wednesday. And the last hands-on is going to be on deep learning, just to show you how to train some models. Okay? No. I mean, if you have questions, you can post them on Piazza. So usually if I see a lot of students have questions, I will hold like some emergency office hour.
Well, I have one quick question. If you can answer, when we're doing doing the compute method to find k, you need to put an input of like 2x vectors, and when we're doing it in the fit method, like doing 1x, we do x and y or x and x dot t.
X and x itself. So the same way I done in here. When I computed k. A second.
Yeah, you did like x dot t.
Yeah, but that's just a way to compute it. So